Dear students, I welcome you for the understanding of stability analysis of control systems, in which we are going to discuss the Routh stability criteria. That depends on your gain value or the proportional sensitivity of a controller, the integral time constant, the derivative time constant, that is nothing but your transfer functions for controller values, then whether the system is stable or unstable. That means you have to understand the bounded input. If the inputs are bounded and you will get the bounded output, then the system that will be considered to be the stable. If the system produces the unbounded or unlimited output for the bounded input, then the system that will be considered to be the unstable. So, to understand this stability criteria, one scientist here developed a method, that is the Routh criteria, which gives you the characteristic equation and the stability, whether the system will behave stable or be unstable, that is obtained from this Routh criteria. So characteristic equation, that is nothing but the 1 plus open loop transfer function, and open loop transfer function, that is the product of all transfer functions in the control system when the feedback loop is disconnected from the comparator. So the feedback control system is stable if and only if all the roots of characteristic equation are negative and have the negative real part. So this is the complex plane. If the roots are on the left hand side of the imaginary axis, then the system is stable. That means the roots are negative. If the roots are positive, then the system becomes unstable. That is, then how to develop a Routh array? That is, from a characteristic equation, you will need the coefficients of characteristic equation. All the all the odd elements are put in a first row, that is A1, A3, A5, and all the even coefficients, they are put in the second row. The third, fourth, and the subsequent rows, they are calculated by using this formula, that is cross multiplying the A2, A3 minus A1, A4 divided by the A2, that is going to give you the value of B1. Similarly, the value of B2, that is obtained from cross multiplying the A2 and A5 minus A1 and A6 divided by the A2. Then what is the stability test? The first thing, that all the coefficients of the column 1 should be positive and non-zero. That means the roots lies on the left hand side of this imaginary axis. If the column 1 is all positive, then the roots lies on the left hand side of the imaginary axis. So the system becomes stable. This is the first rule. Then second rule, that is how many times this sign that is going to change. If A1, A2 are positive, B1 is negative, and C1 that is positive. So there is a sign change from this positive to this negative, and from this negative to this positive. That means 2 times the sign that has been changed. So the two roots lies on the right hand side of the imaginary axis. There can be one thing also. A1, A2 and B1 they are positive. However, the C1 that is negative. So there is only one root that will be the lie on the positive side. So there is a pair of purely imaginary roots lying equidistant from the origin element of the nth row are 0, while none of the elements of the n minus 1th row are 0. Then the location of the pair obtained by solving the quadratic equation Ps square plus Q that is equal to 0, where P and Q, these are the first and the second coefficient of the n minus 1th row. We are calculating up to the n plus 1th row. N is nothing but the power of s. So we are calculating this number of rows up to n plus 1th row. N row, n minus 1th row, K, P or Q, and equate it to the 0 that is going to give you the roots. And the limitation of the Routh test for stability is that it cannot be used for transportation lag parameters. It is used only for the systems having polynomial characteristic equations, and when it gives only about the stability or the instability, whether the system is stable or unstable, but it does not talk about the actual location of the roots. Root की value क्या है, that is not obtained from this Routh test. So these are the limitations for this Routh test. Now let us solve the simple problems associated with this, and such simple problems that can be also asked in the examination, objective type. Obtain the Routh array for the characteristic equation given below. Determine if the control system represented by the equation is stable or unstable. So this is what is the characteristic equation, s cube plus cs square plus 2s plus 1 that is equals to 0. Now rewriting this, I can write 1s square plus cs square plus 2s plus 1s raised to 0 which is equal to 0. Then first row incorporates the coefficient of all odd. So 1 and 2 that I am going to put here in the row 1 and 2. Then second row that incorporates the even coefficient, that is 3 and 1. 3 and 1. Then calculation of the B1, which is nothing but 3 into 2 minus 1 into 1 divided by the 3. Similarly, for B2, I can calculate 3 into 0, that is 0. 1 into 0, 0. So this is also becomes 0. Then C1. C1 that is calculated by multiplying the 5 by 3 into 1 minus 3 into 0 divided by 5 by 3. So 5 by 3 got cancelled and it is 1. Now looking at this, all the roots, all the coefficients of this first column are positive. That means this positive and non-zero. So the system becomes stable. Rule 1. Since all the elements of the first column of the Routh array are positive and non-zero, the control system becomes stable. The next problem, that is, if the characteristic equation is 1 plus k upon 15s plus 1 into 60s plus 1. I can simplify this. 15 into 60, that is 900s square plus 75s plus 1 plus kc, which is equal to 0. So this transfer function, 1 plus product of all transfer functions, to obtain the characteristic equation, it is simplified. Now constructing this Routh array, so A1, A3. Now here A3, that becomes 1 plus k. So 900, 1 plus k, and A2, that is all even coefficients in the row 2, 75. So multiplying 75 into 1 plus k minus 0 divided by 75, which is nothing but 1 plus k. So all the coefficients of the first column are non-zero and positive. So the system is stable for all the values of k. 1 plus k it is. So whatever the value of k, positive value of k, that will be there, the system will be stable. Now determine the value of t for the following system, where 1 plus 20 upon s into bracket ts plus 1, 0.1 s plus 1. So after simplification, you will get this equation. Now substituting A1, A3, that is 0.1 t, 0.1 t, and A3 is 1. Then 0.1 plus t, which is the even coefficient, and this is A420. So this is 0.1 plus 1 into 1 upon 0.1 t into 20 divided by 0.1 t, that is going to give you the coefficient C3. Now you have to determine the value of this t for the stable system. So this has to be equated to the 0. I can go up to the, this is for the third rule. I can go number of rows n plus 1. So s plus 3, that will be there. If the system is stable for all the values of t less than 0.1, so t, which is equal to the minus 0.1, so it is less than 0.1. So the next example, that is, this is the block diagram that is showing. From this block diagram, you have to calculate the open loop transfer function first. So product of all transfer functions in the control system, that is the open loop transfer function. Then characteristic equation, that is 1 plus open loop transfer function, that is going to give you the characteristic equation. So after simplification, you will get this as your characteristic equation. Now constructing the Routh array, so A1, A3, that is A1 is 2, A3 is 1 plus kc. They are in the first row. Then second row, all even coefficients, 3 and 2 kc. So A1 is calculated, A2 is calculated, B1 is calculated, and B3 is calculated, because S3, that is nothing but the 3. So number of rows 3 is n plus 1, or here it is written m plus 1 number of rows that is mentioned. 3 plus 4, that is 4 rows. A1, that is calculated like this. A1, that is nothing but 3 into 1 plus Kc minus 2 times 2 Kc divided by 3. 3 into 1 plus Kc minus 2 Kc into 2 divided by 3. So this is 3 minus Kc upon 3, and A2, that becomes 0. Similarly, you have to calculate the B3 values, and substituting this A1, B1. Then the control system becomes just unstable when all the coefficients of the mth row becomes 0. All the coefficients of this mth row becomes 0. So 3 Kc upon 3, that becomes equal to 0. So Kc equals to 3. For the gain or proportional sensitivity Kc, which is equal to the 3, the system just causes the instability. So this is what we have to consider for the mth row. This is the rule 3. If the control system just unstable when all the coefficients of the mth row becomes 0. तो mth रो के कोएफिशिएंट 0 कब होंगे? जब Kc की वैल्यू 3 आएगी तो, राइट? 3 minus 3, that is 0. So the gain of proportional sensitivity Kc, which is equal to 3, the system just causes the instability. Now what will be the pair of roots? The location of pair of roots of this characteristic equation line lie on the imaginary axis equidistant from the origin can be determined using this following equation, that is as square plus b, which is equal to 0, where a and b are the two coefficients of the m minus 1th row, are the two coefficients for the m minus 1th row, that is 3 and 2 Kc. So I have to use these values of 3 and 2 Kc. So Kc value we have already calculated as 3. So 2 Kc, that becomes equal to 6. So this is what the value of S, that will be calculated as plus minus j root of 2. That is nothing but 1.414 j. This is the location of pair of roots of the characteristic equation lies on the imaginary axis. Which is equidistant from the origin at 1.414. Now if I will plot a graph of this imaginary axis, then the values of plus 1.414 plus side, and similarly the minus side, that is 1.414 j. So this will, for the corresponding value of Kc equals to 3. If the value of Kc, that I am making it a 3.